Hi guys, I want to review for the quiz, and the quiz will be on bipartite graphs and matching. And so here you have a graph that I drew for you, and a little bit complicated graph, but okay, not too much. A couple of things you can do with this graph, but what we're going to interested in the first question is this a bipartite graph? Now, as it is presented to you, it doesn't look at all bipartite, right? So bipartite, you kind of think, okay, there's a bunch of no vertices on this side, a bunch of vertices this side, and then there are connections that go across, but nothing on the left hand side is connected to anything on the left hand side, and nothing on the right hand side is connected to anything on the right hand side. Okay, but it doesn't look like that because why not? Remember, graphs, the actual position of the nodes, the location of the nodes, the relative position of these nodes, these vertices and these edges, have no bearing. You can move them around. It's always the same graph. So how do we figure this out? And this is, so the solution is coloring. If you can color the graph in two colors, let's say red and green, pardon, sorry, that no red vertex is adjacent to another red vertex. So the green are adjacent to the reds and the red are adjacent to green, but no mismatch. And then the reds are one of the collection of the bipartite graph, and the greens are the others, the left and right, or right and left, whatever, doesn't matter. Okay, so let's try to figure it out. So let's start with A. And I'm going to call, let's use the colors green. So A is green. No, okay, I want this a bit bigger. Let's make it this big. Okay, so I color A green. But the moment I color A green, everything connected to that green has to now be red. So that forces me to make this red, and this red. Okay, let's be systematic. I'm going to B. I could continue, but I like to go through my list in one order or the other, and since the letters are alphabetic, I'm just going to follow the alphabetic order. Because I have to make sure that at no moment I introduce a conflicting color, two colors that are adjacent to each other. Okay, just putting colors here and there doesn't guarantee that you have not overlooked something. So we have to be systematic. Now, some of these things have not been colored, so we see whether we need to color them or not. Now, B is not colored, but B is connected to H, which is red, so B has to be green. So that already takes care of B. So that is B. Now, what about C? C is connected already to a red. If C would not be connected to anything that I have done already, then I go to the next one, because I don't know yet. I don't want to commit to C, the color of C yet. Okay, I only commit to a color if I have no choice. So, of course, except for the very first one, there I choose something. It doesn't matter if I start with green, then I get one coloring. If I start with red, then I get the opposite coloring, but if it works. Okay, so from the fact that C is connected to J, which is red, I need to color C green. Let's look at D. D also is fixed because I have no choice. D, because of the redness of H, D has to be green. Okay, now but now I have to look here. I colored D, but there's another thing, another neighbor of D that is already colored, that is J. Right, it's kind of a little bit long connection here, but it is colored. So, and the color luckily doesn't clash. That's the whole point. Okay. So next one is E. E, well, E, it has to be green for two reasons, and that's the only two reasons. So everything works out as long as E is concerned. Finally, no, not finally. Sorry. Next F. What about F? F. Okay. F is directed to K. So we have this connection here that forces F to be green. And anything else is not connected to F yet, so I can wait. F, G, okay, G. G has to be red, because I have no other choice here. It is connected to that green C here. H has already been red, and all its neighbors are green. So perfect. H, keep it up. I, its neighbors are all green, so I has to be red. Okay, great. And so no conflict here. J is already being colored, and look at all its neighbors, they are green. Perfect. I, J, K, same for K. And about L, L is not colored, but it is only one way to color it, is red. So yes, this is a bipartite graph. So this is, we can say, V1 is A, B, C, D, E, and F, right? The green ones, or V green. You can call it V green if you rather work with colors. So this is V green, and then V red. Hey, I guess playing with colors is sometimes a bit too tedious. Are the letters G, H, I, J, K, and L. Now, do not conclude from the fact, oh, they are alphabetically the first ones and the next ones. That is no guarantee. That is just, okay, I labeled them that way, so it makes it later a little bit easier to work with. But in principle, the names of these nodes have no bearing on the connection they have in general, right? Okay, so we have that. Second question is now, and this is is there a match? So now that we have V1 and 2, they both have 6. So if there's a complete or perfect matching, then it will be 6. The 6 guys, the 6 green guys will be matched with the 6 red guys. So is there a perfect or complete matching? So this one, how do we solve this? This I'm going to ask you to use the marriage theorem. The marriage theorem. Now, what the marriage theorem says is you have to look at neighbors, not only just of one vertex, but neighbors of 2 vertices, of 3 vertices, etc. And then what you need to have, so there are 2 possibilities. If for all subsets of the green ones, so V green, sorry, I'm gonna keep V green, of all the green nodes, but all subsets, not just single ones, but perhaps 2 or 3 of those, if the size of the neighbors of that set is bigger than the size of the set itself, then yes. If not, otherwise no. So this is the thing that we have to check. That's the marriage theorem. If we have this inequality always happening, then yes. If it's not, then no. Now, what is easier here is, of course, finding a counterexample. So if we can find a set that doesn't satisfy this property, in other words, the set has more elements than it has neighbors, and that's because then remember, the neighbors, what are the neighbors going to be? They're always going to be red, right? Because it's a bipartite graph. So these are all green stuff, and these are going to be all red guys. So if there are more green here than red here, and these greens all have to match with a neighbor, and the only neighbors they can match with are these guys, there are enough of them. Okay. So how do we figure this out now? Well, the best thing to do is to make either the adjacency table that we discussed today in the lecture, or just draw the neighborhoods. I'm going to just draw the neighborhoods here. So here's the neighborhood, or calculate the neighborhoods, and here are the vertices, the green vertices. Okay, let me write the green. So we have A, B, C, D, E, and F. And so what is the neighbor set? So the neighbors, so here is the n of A, so this is n of A here. So what are the neighbors of A? Well, we see that is J, let's do it alphabetically. That's going to help us a little bit understanding what goes on. H, J, K. The neighbors of B, I'm just reading off from my graph here. The neighbors of B, that's only one neighbor, H. The neighbors of C, G, J, and I. Okay. the neighbors of D. D has not that many neighbors, right? H and J, the neighbors of E, H and K, and then finally the neighbors of F. F has, where is F? I, L, I, K, and L. I, K, and L. Okay. So we're looking for now a set of this sigma is a collection, is some of those. Now, if you take all of those, it's not going to work, right? Because what are all the neighbors of these guys? Well, these are all the greens, so all the neighbors are all the reds, and there are as many greens as reds, so we have this inequality. Also, if I just take one of them, it's not going to work, because then this quantity is just one, and this quantity is at least always one, because the sets are not empty, the neighbor sets. So I cannot take everything, I cannot take just one thing, so that's the whole point. Which set do I take? There's quite a lot of combinations, right? Should I take D and E? Should I take B, C, and F? All these combinations. Now, what are we looking for? We're kind of looking for, perhaps, are there three, let's think of it, what we want. First of all, what we could look for is two nodes that have only one neighbor, and that's the same neighbor. But that's not the case, because there's only one guy that has a single neighbor, a so-called pendant. There's only one of them, so no, that doesn't work. So what about if I take three of these guys, but they only have two different neighbors, right? So then this set would have three elements. Sorry, this set would have three elements, but the neighbors would only have two elements. Sorry, I'm pointing to the wrong side. Okay. So is that the case? Well, H and J, but no, H and K. So this, no, okay, so no. But wait a sec. H and J and H and K and H and J and K. So far I only have mentioned three red guys, yet these are sets of four different neighbors. That's what I need. So let me mark this, that you see. I'm going to use this guy, this guy, this guy, and this guy. So let me write it down. So it's really searching for it until you find it. What are the neighbors of A, B, D, and E? Of course, I can go back, look at my graph, but I have it neater on my table. It's easier to see my table. Well, as I just said, it's only these three guys that appear in the neighbor sets of these four nodes, right? So this is my sigma. This is going to be sigma, and the size of sigma is 4. And this is the neighbors of sigma, and the size of these neighbors is 3. Sorry, the neighbors of sigma. I wrote sigma, the neighbors of sigma. The neighbors of sigma has only size 3. So we have 3 is less than 4. That's the opposite of what we want in the marriage theorem. In the marriage theorem, you should always have the other way around. So therefore, since there is a sigma where it doesn't work for, then means we are in this case, means, no, there is no matching. So only finding one example here like this already tells me, okay, no matching. And then you could ask, well, if there is no complete matching, perhaps can we find maximal matching, the biggest possible matching? We know it cannot be all 6. That we have now learned. That's what the complete matching says. That would have been matching all green 6 guys with all red 6. We cannot do that. So perhaps can we do at least 5? Well, we could try that. And so what we see is, I'm going to do the matching in this color here. Now, the first thing what we should look for is for things that we have no choice. If I want a matching that involves B, and I would like to have as much as possible, I have to match it with H. So let's do that. So we're going to mark, this is, if any maximal matching, this one should be part of it. Okay. Okay. Now, if I erase H, so let's do this. So H is now gone, right? So we don't have this anymore. Now we are same thing happens now. D and E have no other place to go. So let's match D with J. I hope, yeah, that's going right. D with J, right? That is because, right, these are the two only possibilities, and H is now already taken, so D goes to J. But if I do this, that means, sorry, that means that J is gone too. So now J is gone from all my lists. Okay, yep. Okay, so what we can do? Well, both A and E have now only one left, and that's because notice that A, B, D, and E are the ones that where I got stuck, when I'm getting stuck, and that's no surprise because that was the set that I found where I got stuck. Where is it here? That's the set where I got stuck, right? So it's no surprise that this happens like that. So okay, so K, well, I can choose now, and because opposed to a complete matching, well, that's not even true. This, even if there is matching, there's never said that they have unique matchings. Okay, that's a different thing, and it's a much more complicated problem if you want to so-called optimal matchings. We'll talk about that later, I think. Yes. Okay, so I'm gonna match A. I like A. I'm gonna match it with K. Okay, so A with K. So the K is gone now too. K is gone. K is gone. So what else? I can still match C with, okay, now I have to think, what should I do? Well, I can match C with G. I think I have a bit of freeway here, leeway. So G is gone, but the G is only appears once, so that's not a big deal. I can now match F with I or L. I'm going to match it with, let's see, what's the shortest? L. Okay, L got lucky. So L is out. And now I has not been matched. It's normal because it's not a complete matching. One red guy is going to be left out, and what is the other guy left out is which did I not match now? Lost a little bit track of which I didn't match. E. So L and E are the two dots that have nobody to go with. All right. So that's the quiz, and the quiz will be very similar. But I stress, I want you to do the marriage theorem. I agree that you could also try to just find a complete matching, and once you have one, you can say, okay, yes, there is one. But perhaps if you have to find a complete matching, that's one thing. But if there is none, that's much harder to show there is none, unless you use the marriage theorem. Okay, and then it's not so hard because you have to give only one counterexample. One set like this, the one that we had here, where its number of neighbors is smaller than the set itself. All right.